Well, thank you very much. It's a pleasure to be back here. And this is a talk that I've taken from parts from three different talks, plus some new material. And I tried to put increasing controversy towards the end. We'll see. But I made the title up by combining titles from two talks, but in particularly with emphasis on the fact that they're going to disrupt lives here by tearing up the parking lot and start building a new building for quantum computing. And so let me start on that. You would think with quantum computing, since we can in theory run complex simulations that have many variables and they're relevant to the field of cosmology, this would really be a noble application of quantum computing to trying to understand in cosmology, particularly the beginning when quantum effects might be very important in the universe. And so already people are being excited about doing that in this field. I'm going to give you some examples in which you realize the lofty goals are fallen far short from it, okay? There are a couple of articles by Kaufman and McCohen about, quantum computers for the early universe and quantum computation for early universe cosmology. It's a nice outline and it's, but it doesn't produce any new science or anything like that. There is among one of our collaborators, or two of our collaborators, on a paper that we just recently published, and I had expected Tom to give a talk later this afternoon to talk about that paper, so I have to stick some stuff in. So that's in the middle where it's partly controversial and partly not. But that doing quantum computations is really relevant if you're looking at things like wave dark matter especially, but in some other things. But again, this is a thing where people have outlined what's going on, but they haven't really achieved any major kind of stuff. There was a big splash about a month and a half ago by a team from Caltech, headed by Maria Spyropoulou. They claimed that they had shown how information can go through a wormhole. Now that's a big controversy in some other aspects of information theory and so forth about whether information can pass through a wormhole. They made up a quantum circuit that was a wormhole, but the wormhole solution wasn't the standard Einstein-Rosen wormhole. It was one that the Caltech group had made up, and it's stabilized on either end by a ring of negative energy that then allows it to be a stable wormhole and you can transfer information from. And they showed they could do it. Now, these guys were supported by Google Quantum AI, and their competitors were supported by IBM. So you will notice there's a double controversy here. There's a controversy about whether what they did is right, but there's also a controversy between the Google quantum computing guys and IBM quantum computing guys. And so it's a big discussion that goes on in the literature at the time, and it went on for about a week and a half, where everybody was claiming that, no, you didn't do it right, and this is how we should have done it, and so forth. That's one of the things you see, that in the early stages, there is a big push from the science, but there's a big push from the commercial side, because the commercial implications are quite large. And I give one more example just because I have a student who she's getting ready to defend her thesis on August 12th, who I never could wean from black holes. And so she's been working on black hole superradiance and done a very nice set of results and papers and shown how you can make it like hyperfine splitting an atom. You can have fine structure, hyperfine structure. And so she's doing a very good job in that. These guys made a two-dimensional black hole, that's the bottom right corner, a two-dimensional black hole, not a three-dimensional black hole. And they were surprised to see that when they made the circuit to do that, it would start radiating, giving off light at great rates. And they say, it's superradiance. But superradiance only happens for spinning black holes, and so it's again a controversial kind of thing. So we're in the very early phases of that, but it's still going to be important, and it's parallel in the development of our ideas on the fundamental edges of physics and cosmology. So I'm going to give you a little quiz. I did this last time for the Search for Knowledge, but I gave a somewhat different quiz. You're going to realize that information theory and what we're doing in the quantum part of cosmology is highly related. And that's what I'm going to try to get to at the end of the talk. So the quiz is, what's the quantum no cloning theorem? For those of you who are experts or have already heard this quiz. What about the no deleting theorem? Why is the Chinese government investing billions of dollars USA because of the no cloning theorem? And there's a hint up in the upper right corner with Alice and Bob and about why they might be doing that. Then there's a no hiding theorem in information theory, which says that quantum information is never lost but conserved. Now this is a tricky issue because it talks about basically entropy being a conserved quantity in the universe. And yet we're used to entropy increasing by the second law. And so what do we mean by entropy increasing and what do we think conserved? And that's an issue that really comes down to the fundamental physics of what space-time is. Okay, and how do we get around these theorems, particularly the no cloning theorem, where you can't just make a copy of an arbitrary data set, arbitrary problem, and store it. So if the thing crashes, you can just start the calculation over again. In normal calculations, we do checkpoints every so often, and if the computer crashes, we just start from that last checkpoint and just keep running. We don't have to do all the calculation. But for quantum computing, we don't have a way to do this unless you use some kind of cleverness to get around it. And at the end, how does this show that the universe is really simply a quantum computer? Right? So that's the more speculative stuff I want to get to at the end. High power computing has been playing a computational role in cosmology because it allows the researchers to analyze vast amounts of data, to make really complex simulations, I'll show you examples of those, and model the behavior of the universe, comparing the data with the simulations. And this has actually been a driver of high power computing for more than 2 decades. Only recently have there been problems that are as large as the problems that cosmology does that are in the large language models, but they're simpler in a certain sense. Whereas in the computer, we're doing 10 million, tens of millions of elements, but in the large language models, they're up to now about 1 trillion, it's almost 1,000 times. However, they don't have to solve it as carefully, they approximate. So in the large language models, you're trying to find, 1 trillion parameters, but you don't think you have to get all those parameters right. You just have to get them roughly right, and they let you run your large language model. And that's because you have a different standard for what you consider a proof and so forth. So where are the areas where high power computing is most important? Well, it's analyzing the observational data. We're now having quite commonly terabytes of data coming from telescopes or from satellites daily, on a daily basis. Data is coming in at a very high rate and it's having to be processed and dealt with and categorized in that kind of way. And that comes from the cosmic microwave background, comes from galaxy surveys, it comes from a number of observations that are going out there. This is actually really one of the main things that drove computers, because before people were trying to find the largest eigenvalue of a chemistry problem or something like that. We were trying to find every value. And that required, people making really high quality parallel processing systems that parsed the data out, did the matrix conversion, and then pushed the data back together and so on. But the really high power is run now in the simulations of the universe. And I'll show you some examples of simulation. Those simulations cover an incredible range in time and space over very large numbers of pixels or particles or whatever samples you want to. And those are really events, but in the end, you end up comparing the data and the simulations. That, again, ends up using a tremendous amount. And so up until 10 years ago, or a little less than 5 years ago, these kind of things were driving the high power computing. And it's only now the large language models are pushing harder than that, and they're very efficient and sloppy, and they use up more electricity, more electric power than other kinds of things. But still, these are some of the primary drivers. And so the thing that's amazing about that is, here's the example from Planck. This is a Planck map on the right. It's a map of the variations that are roughly 10 to the minus 5 level fluctuations in the cosmic microwave background. And it's a 10 million pixel map. That meant there was a 10 million by 10 million matrix that had to be solved and inverted along with there's its parameters and a bunch of other stuff. It's all reduced down first because of isotropy. You can collapse the 10 million, right, from area to linear, and then you get a power spectrum. And then you can collapse that down to just 6 numbers. And these 6 numbers are now measured with fairly high accuracy. They're the physical density of baryons, the physical density of dark matter, the size of the fluctuations on the horizon, the various things that you're the tilt of the spectrum. Those few parameters are able to describe this with very high accuracy. But now the question is, are they sufficient, or is there something new or something else coming up that we need in order to explain that? And so here I'm giving the sort of the example, but astronomers do everything backwards, but that's we have to get used to that. But if we look on the very large scale to the very smaller scale, 10 to the 12 solar masses versus, much higher, out of this region, you see there's a power law. And this power law is essentially a unit power law in terms of what's going on. And then it curves over and it rolls off to another power law. And this is, if it wasn't astronomers, this would be, if you were doing it in what I consider a more fundamental thing, curvature of space-time. This is flat curvature of space-time. That is the original, inflation or whatever caused the creation of space-time, creates space-time and creates with quantum fluctuations that are roughly 10 to the minus 5 level, and they're almost independent of scale. There's a slight red tilt. And then there is a roll-off region where things are going. But in here, you see little tiny wiggles. These are the baryon acoustic oscillations, which we see so strongly in the cosmic microwave background because that's what you see when the light's released. You see it later in the formation of huge spheres of galaxies around the really big clusters of galaxies. And then this is the roll-off, how things got dissipated at lower time. But we have observations now on all these scales, and it's a pretty simple curve to fit. And even the wiggles are things that we predict ahead of time based on our simple understanding of what's going on. Okay, so here's the simulation. You can see the simulation is hard because at the beginning, the universe is expanding, and the universe keeps expanding, but a certain region will eventually get to the point where its own self-gravity will cause it to collapse back down, and you will get the formation of what we think of as a galaxy or a cluster of galaxies. In this case, we're looking at this thing in a box that's 2.4 million light years across, and you can zoom in and see how it looks. And what you see is this kind of relaxed system, but you also see there's a lot of structure around it. There's a lot of substructures. There's a lot of gravitation collapsed things. And this also has a power law. And this is something that we have to try and explain later on. And this is one of the reasons that we're doing some unusual things. Recently, the Flamingo collaboration come out with what they claim is the largest ever cosmological computer simulation. From here to here is about 10 billion light years across there. And they keep track of the gas and the gas temperature because they want to see the X-rays when you get ionized gas. So they keep track of the X-rays, you study effect from that. Plus they keep clear of the dark matter density. So in this simulation, you're not only simulation over a huge expansion of the universe and a huge volume, again, the 10 billion light years, you're keeping track of a huge number of particles that are test particles that are simulating what the gas and the dark matter are doing. Right? So let me show you that simulation. Right? And it's just the dark matter down at the bottom. This is the gas at the top, and you can see the redshift and you see the time going on. Now the thing that we're excited about is because of DIPC, we're looking back to seeing galaxies just forming around z equals 13. And so before we were seeing stuff as equals 7, but now we're seeing stuff as z equals 13, and that's approaching the limit in where galaxies form. But as you can see, stuff is going on all the time, right? The question is, do we set the time scales right? Do we set the scales right? Do we really see what's going on in these simulations, or are we missing something in terms of what's happening? So, I mean, this is going over, the 14 billion gigayears to the present redshift to 0 out to the redshift of about 14 at the beginning. So these simulations, these are outgrowth from the Millennium simulation. Some of the people here are using Millennium simulation to try and understand about the bias on the formation of galaxies. But if you look, here's at the end of the Millennium simulation, and here's what I think the present day universe looks like. And it's zooming in, of course, on this biggest structure. But there are all these voids around here too. It's a very complicated structure. We started with an almost uniform universe, but it really separates itself out quite substantially. And if we lived in a cluster like this, the difference between us and Andromeda is like this distance. We would see a very different looking universe out the window. Okay, so now I'm going to talk about some data. So conveniently, the DAISY survey released the first year of data very recently. And so it's part of what I regard as the Moore's law of galaxy surveys. Okay. So in the bottom corner is the plot of time, unfortunately it's cut off because I ran off the edge, versus the number of galaxies. And you can see Moore's law would be that straight line hinted at in white, and you can see the various ones, and you can see the DAISY survey, the dark energy sky survey, being up at 40 million. And the answer is it's actually going to be higher than that, because now the first year is released, but there's now 3 years of data in the can. So the interesting thing, the data were released, then 3 years, just the next week, 3 years got in can, and the next week, the tray that holds the 5,000 fiber optics that go to the 5,000 little robots that position on each galaxy fell. It cracked. It fell off and it stopped. But yesterday it started again. So you'll be back and it's still on survey. So what's relevant is you're going to see the 10 billion brightest galaxies, the ones that are nearest us, and then, 10 billion, and then you're going to see up to 40 million, no, probably 50 million. And beyond that are quasars, and you're seeing their light being absorbed by the Lyman alpha force. That's the whole strategy. So you're going to expect by the end of the 5 years there will be 2.5 million quasars, plus their absorption lines, plus they're going to be roughly 50 million galaxies surveyed. But it's not just surveyed, it's spectroscopically measured. So that's a huge data cube if you think about what's going on. So here is the first image released, and you can see some imperfections in it. There are some places you see it here. So this is the Lyman alpha forest, and then this is the region in between, and this is the nearby one out to redshift about 2. This is what the galaxies look like. You can see some places are missing because there were storms or other things, and they weren't able to survey during that time period. That'll be redone as the thing keeps going on. That kind of stuff will continue. So this is all being done from Kitt Peak in Arizona. You can see the telescope, and here are the nearby galaxies, and then there should have been a Lyman alpha, and then way out here, it's got the microwave guy. This is just to be artistic, but it allows me to put on the bottom that there's 5.7 million galaxies in the first year's release. Those 5,000 at a time add up. When you, if you do it 1,000 times, you get 5 million, right? And that's a huge amount of data. You realize that means when you're dumping that data, you're dumping 5,000 galaxies and 5,000 spectra each time, and you're doing that time after time in a night. There are already 400,000, 420,000 quasars, and therefore Lyman alpha forests in these data so far. It's a big step forward, but this is only 1/3 of the data that now exists on disk, right? I mean, there's still be processing. And so here's a rotating wedge, just a section of the whole thing. And every one of these points is a galaxy where you can have an image of the galaxy, but also the spectrum of the galaxy. So this is a huge data cube if you think about how many dimensions it is or how you want to parameterize it. And it remains to be analyzed and to process, but there's a lot of activity going on in this regard. Let me call out one of the results that they made a big deal about. That is, if you think about the equation of state, if you have a fluid, generally you characterize it that the pressure in the fluid is proportional to the density. So W times the density. So W here we're going to parameterize to fit, or to the W at the present time plus WA times 1 minus A. Now, I personally am responsible for that configuration from long ago because Eric Linder was writing a paper saying, let's do W plus WZ times Z, right? How it varies with Z. And I said, I've put too much emphasis on the really high Z's. It's going to force the thing down if that's the answer you want to get. If you want to see it more, you just make it WA. And so we did, but now that puts a different emphasis on it. But the different thing is, if you look at the raw data, it looks like it's seeing that the equation of state is not constant. But it's not very much. It's less than 2 standard deviations, so it's not so much. It's kind of hinted at, and here in blue, it's just close to 2. Right? So on this plot is W minus 1 and 0 is what you'd get for a cosmological constant. You can see it barely, the data, DAISY data by itself, the first year data, only barely includes the cosmological constant. But if you add any of the 3 sets of supernova, you get a value that's deviated either at 2.5 standard deviations up to 3.9 standard deviations. The 3.9 is starting to be something to worry about, but I think it's early. Fortunately, there exist 2 more years of data in the can, but it's going on. But it's clearly the supernova that are also driving this down a little bit. Now, I'm emphasizing this because it's a big deal if the cosmological constant is not a constant. If it's not a cosmological constant, it's some kind of dark energy, then why is it behaving and changing on a time scale that's proportional to the present size of the universe in a certain way? Well, it doesn't necessarily. That's what happened when you just do the first order of expansion, right? You'll see what's going on. And the other thing that makes me concerned about this is you now look at what was advertised as double tension, which is the projection fitting the data observed to the Hubble expansion rate, which is high and goes down to a minimum and comes back up because the universe is accelerating. You fit that and see what the point is for its present time. Then you see that the C and B is giving a relatively low number. Grand acoustic gas station, Big Bang nuclear systems got a relatively number. These 2 new results from DAISY getting a moderately low number. The tip of the red giant branch is getting one consistent with either one, and then the relatively nearby supernova, although they go out to redshift for 1, they're getting a value that's different. So I am suspect that either there's somehow these guys are overlapping now. The pairing acoustic gas stations go down to almost a redshift of 0.3, and the supernova go out to a redshift of almost 1. There's overlap in the time periods, so causing it nearby and far away isn't really quite the right thing. It has to do with how you fit the parameters and how prejudiced you are. So I still suspect about whether there's a controversy or not a controversy. But it really does matter if there really is a change in the equation of state. That is a big change in what we think about our cosmology, right? Why is it? How is it that some energy in the universe is changing in the present day, and it's a very low energy, right? It's a 10 to the minus 122 of the Planck energy. Let me talk a little bit about the draft dwarf galaxy problem. And that simulation I showed you of the dark matter. The dark matter has this core, relaxed core, but it has all these small compact objects around it, gravitationally compact objects around it. When we look at our own galaxy, this shows you how old I am. When I was young, there were only 6 known dwarf galaxies around us. And now there's 25, but some of them were hidden behind the plane of the galaxy. Some of the people just hadn't searched in those areas. But still, there's only 25, and there should be 1,000, right? It's not quite right, but it's there's a big gap between the number of dwarf galaxies we see around Andromeda and the number of dwarf galaxies we see if we think that lambda CDM is the correct model. So there are solutions that people had. You blame the astrophysics. You say the formation of stars blows the stuff apart and that keeps it from happening, whatever it is. Or you blame CDM. So this is what this is. This is constant curvature, which is density variation proportional to K. Constant curvature, and then the roll-off as you dissipate energy. And if you make warm dark matter, it can escape earlier, and therefore you lose you lose the fluctuations at higher scale. So you can say, all right, well, we'll make it in warm dark matter. Well, that kind of works and it doesn't work. One of the problems is when you look at the Lyman alpha forest, the early results are kind of tricky, but if you compare what you predict from lambda CEM and from the warm dark matter with low power, you see there's much less high frequency power in it. Yet when you look at some of the spectra you have, now we're going to have a lot more, when you look at some of the spectra, there seems to be some high frequency power in there. So there's a controversy that people don't really like the warm dark matter so much because of this, but this is also data that are still a little suspect in terms of how well they've been processed and analyzed. I've been working with Tom and colleagues here on maybe the dark matter might be quantum mechanical. It's a very light particle on the scale of 10 to the minus 22 electron volts. That gives it a Compton and de Broglie wavelength that's comparable to the size of the core of a galaxy or something like that. And that ends up causing a number of things. It makes the equations much harder to solve, so the relations get more difficult. But also, it creates basically a de Broglie pressure, or uncertainty principal pressure, that keeps the dark matter from clumping too seriously in the centers of galaxies. But it's a little more complicated than that. And Tom is very much a pusher of that because he and his colleagues wrote some of the first simulations. So here's one of the early simulations showing how galaxies and clusters and filaments of these wave dark matter would be. Plus, if you look way into the core, you're going to find the soliton that's at the center, and then around the soliton are orbiting parts of the same boson, but in higher excited states, or higher eigenvalence states. And so here's a simulation of how that looks, just to show you the kind of thing. You can see there's extra wiggles and stuff going on, but there's extra pressure that stops the condensation of the matter in the early core of galaxies. And if you look at the simulations very carefully, on the top, you'll see what the weakly interacting massive particles, or the ordinary end of CDM, looks like, and on the bottom, what the wave stuff looks like. So here you see it, and here you see the wave, the effects. You see the same, they have the same seeds, you see the same kinds of structures coming out, but it looks very different, right, in a certain sense, because it's spread out. Likewise here, you're looking at the dark matter, the gas, and the stars, the dark matter, the gas, and the stars. You can tell it's similar, but it's not exactly the same thing here, right? These guys are obviously similar, but they're not exactly the same, and you avoid the really sharp cusps and so forth that you see. And we had a postdoc here who's been working on trying to do two fields at once. Two fields turn out to be much more complicated because there are instabilities. The two fields can be unstable between each other, but he's done some simulations, right? So we can blame the astrophysics, we can blame the cold dark matter, or we can blame the observations, but nobody blames the simulations. You notice that. But the simulations could be blamed too. And it's clear we got to be more careful, right? So you can probe, we can do gravitational lensing, and I'm going to show you a little example of that. And this is an example of the cusp. If you imagine that you have a galaxy or a galaxy cluster here, you have your source way behind, and you're looking you're over out in the audience looking. As you pass behind, there's a certain place where you're going to get an Einstein ring or a cusp. You know, if the galaxy cluster is oval, you'll get a little more complicated thing. But you get a cusp where the manifestation is trying to go towards infinity. And with WIMP dark matter, you get a cusp that looks like this. But if you put different kinds of wave dark matter in, you get wiggles because you have to have the de Broglie wavelength, perturbations in what's going on. And so this is a paper that we put out a year and something ago. But then this came up. This is a paper we put out last week. And Tom showed me this picture of the Dragon arc in Abell 370. And the Dragon arc is going to eat up a lot of stuff. It eats up all the primordial black holes, eats up everything. The Dragon arc is this very spectacular thing. This is the cluster Abell 370. In cluster Abell 370, you see the arc. If you look down below, you'll see there's another arc, another arc. There's one up here, one there. And I say, all right, I send a note back to Tom. I said, don't get all excited by the dragon arc just because it's fat. The other ones are really thin, you know. Because I knew for sure he was going to say, yes, it's wave dark matter, we can prove it. Yeah, so the answer is, of course, people started finding stuff. They started finding micro lenses around it. So this is being lensed by a galaxy or the cluster in front of it. If stars or objects pass through this cusp region, through this part, they will cause this to be modulated and seen. So this is a picture out of that paper, right? Both in the Dragon arc, both from JWST and HST. There are a huge number. At the time there were 35, now there are 50 of these micro lenses or milli lenses, depending on your viewpoint of how big a source it is. And they seem to show up, showing that it's sort of predicting what you say. They would broaden the Dragon arc, and they would preferentially be on the inside with a negative parity image. I have to apologize to Tom. Yes, you did, as I said, you were going to write a paper about it. But yes, at least there's some interesting things about it. So I'm just drawing your attention to that because I want to move on to the other stuff. But there are things you can do. This just shows you what happens when you get to the Einstein ring, and then this is a radio measurement of it. You can see these rings. You can, if you were lucky enough to be in a cusp and have the telescope doing a cadence on it, you could look for these stars and star clusters and stuff passing through the cusp and changing the magnification, and they tell you a lot about what's going on. And there's a cusp problem, which has been known for quite some time, that dark matter predicts too much density in the center, whereas the measured density in the center of things is just not as high as it is. So what does that all mean? It means either we didn't do the simulations right, that is the more stuff we got to simulate, or there's some new kind of physics, a new way of thinking about stuff. So we know a lot, we understand some. That's the underline. And lambda CDM is actually very compelling because it can describe a lot of things, but it isn't definitive yet. We haven't really proved that that's the correct thing. Predictions of the universe are very interesting, but when you start making predictions about whose quantum computer is the best, that's yeah, we're going to have to be more careful in the future. Okay, so now I want to get into the really controversial part. So I want to talk about the holographic principle. You'll see why this comes back, because this intersects both ways in cosmology and in quantum computing. The holographic principle is a confusing way of saying we actually live in one less dimension than we think. We think we're three-dimensional creatures, but we're actually two-dimensional creatures. I know I have trouble with this. I know how Bohr and Einstein, those guys felt when they were calculating stuff and they got one answer and their intuition told them a different answer. So it is almost unassailable, unless you break one of our most sacred laws of physics, that we are actually two-dimensional beings. So this is the part that's controversial in my talk. So first I'm going to entertain you. For €100, you can buy this, and it works outdoors. It's pretty nice. Sorry, I shouldn't hit the microphone. They look like quasi four-dimensional, three-dimensional horses going on. That's a better fish, right? But it's impressive you can get this for €100. So this is coming from a two-dimensional, basically video information that's being projected into real three dimensions. That's the problem. There are real three dimensions here. There's another, if you got a lot more money, if you got $2 billion, you can make this kind of a system. This is a sphere in Las Vegas, and they spent a huge amount of money. And they have a big screen area where they did the YouTube concerts and do some other stuff now. But it's really quite spectacular, the thing. And they've gone to a great effort to make those holograms extremely realistic. They didn't, not all of them were realistic, but some of them were amazingly realistic. But I don't know if any of you have seen the three-body problem. I highly recommend it if you're interested in this kind of thing. some of the leading scientists and people on the Earth are given these headsets by aliens who are actually quite far away. And they're given to them by their intelligent computers that were unfurled into many dimensions and turned into AI systems, quantum computing AI systems, and folded back up. And they could then travel at the speed, light speed to get there. They give them this kind of a headset. And this headset gives you a virtual reality that's extremely real. Okay, it is really high technology. It needs more apps. It's only one problem they're trying to solve, which is the three-body problem, which we know from physics is a problem that's insoluble if the mass is, if it's arbitrary sets of masses and so forth. So, if you haven't seen this, I recommend seeing it. But this is getting closer to the real holographic principle, which is this is in your head. This is being projected into your head and your feelings and your tastes and so forth. Here's the holographic space-time. So in 1981, Jacob Bekenstein wrote an article in which he gave clear arguments why the amount of information that can be stored in a volume is bounded by the surface of a black hole. That is, there's a certain amount of information you put on the surface of the black hole. They had figured out the entropy of the black hole. And that entropy was a sort of a second law kind of entropy, the kind of thermodynamics entropy. But the information entropy, also quantum information entropy, is the same thing. And that quantum information entropy is that you are limited to the amount of information that can be in any volume is limited to the area of that black hole. And if you had an object whose part of one of his arguments was if you had an object who had more entropy in it than existed in the black hole in the same volume, and you lowered that into the black hole, you could gain work out of the whole system and violate the second law of thermodynamics. You could turn that entropy into useful work. Right? And that there's an argument. And when I was teaching the first time I was teaching this, I was teaching the students about black holes and thermodynamics of black holes. And I gave the example of an advanced society that's on a sphere enclosing a black hole, and you lower your waste heat in. And you're turning the waste heat into useful energy all the way until you reach the black hole surface, but you can't get the wavelength longer than something that's in the scale size of the black hole, or you can't drop it in the black hole. So you end up having a minimum temperature and a minimum wavelength, and you therefore show that there's a temperature and an entropy that the black hole must have. And that's similar to the earlier arguments that Hawking and Bekenstein gave when Hawking was driving the temperature of the black hole. So you have to think about for a while what it means that all the information that can fit in a volume is limited by the area of the volume, not by the volume. You would think if I have a volume and I have a way to store information in it, I could just put more chips into my computer and I have more stuff to store. But I can't. Right? It violates the laws of physics to do that. The information has to reside on the surface of the black hole. This is a really important implication, and Gerard 't Hooft and then Lenny Susskind got involved in it. Lenny Susskind spent a bunch of times proving a bunch of theorems that quantum information is never lost. That's part of the thing, but that's a unitary. It has to do with the operations of the unitarity, but it also has to do with the nature of things. And once you do that, you run into this problem, right? And they were so much writing about this for some time period that in 1998, Juan Maldacena proved a nice theorem. He said, if you have a 5-dimensional anti-de Sitter space-time that has superstrings and black holes and so forth in it, surrounding that is a 4-dimensional space-time. And on that 4-dimensional space-time, you have conformal field theories and you have some hot radiation. They're exactly equivalent. Okay. So this theorem is very tight and very good, and it shocked people. Some of the people kind of knew it, but when the theorem, it shocked people because what this tells you is you don't know which of these is the fundamental theorem. The string theory or the conformal field theory, right? They're exactly equivalent. It's like two different ways of doing it. But the fact is, all the information that's here is here, and vice versa. But there's also some other very nice properties that there are certain problems that are easy to solve on this flat space-time that are hard here, and vice versa. So it's sometimes for physics problems, it's more convenient to do it here, and sometimes it's more convenient to do it there. And so this has got people quite upset, but it was a long time coming to, but it comes back to the question of, can we possibly really be two-dimensional? That's the issue that because it sure feels like 3 dimensions, right? And here is an example where in principle, you could sometimes prove the theory on the boundary is more fundamental than the theory of the interior or vice versa. And that's a tricky question. If we could prove that, we don't know. Or if they're equivalent, then it doesn't matter because they both give the same answer. Okay, so it took me a while to understand this. The entropy of the horizons is always maximal. If you take a black hole, and in my case, when I'm thinking about the universe, and apparently I was the only one thinking about the universe those days, but everybody else was thinking about the black holes when they were coming from, you will always have the maximal entropy on that boundary, and it will be related to the energy and information content on either side, right? That is, if we have a horizon to the universe or a horizon to a black hole, the entropy on the black hole is related to what's on the other side that we can't reach. I've been, thinking about this problem for a while. You used to say, well, we could drop a proton in and it would lose the baryon number. I think not. The baryon number stays on the surface of the black hole, and at the end it comes back out. And likewise, if you throw a student or an astronaut or a robot into the black hole, the real information will stay on the surface of the black hole, and some modified copy, or some crummy copy, will go in if there is continuation inside. So it's a tricky question about what really happens when you cross the boundary of a horizon. Right? How does that information get stored on the horizon? And we'll see. There was already, before this, proved a set of 4 theorems by Hawking and Penrose and Hawking and Ellis, which were called the 4 laws of black holes, about how black holes only grow in size, the entropy only increases, all this kind of stuff. And those 4 are exactly parallel to the classical thermodynamic entropy laws. And now you have it after Hawking. You've got a temperature and you've got an entropy. It's going to come out, and that entropy comes out right here. And it was considered, some years ago, it was considered a great success by string theory, that they could predict that factor of 4, right? But we can see. But that factor 4 really, really matters. It says, if I'm looking at a surface of a black hole, and this is a Planck size, that it's really a triangle or whatever, something that's larger than a Planck size, 4 times. And not long after that, Ted Jacobson wrote a very interesting paper where he showed that you could derive general relativity strictly from the delta Q equals T delta S relationship from thermodynamics. And it had his proof in order to get the full equation. You can get sort of Newtonian physics with the sloppy argument. You basically set up Rendler spaces. Rendler spaces are constant, acceleration spaces that are going on this kind of stuff, so that there's a horizon, a Rendler horizon. And that Rendler horizon will have an unread temperature, and that temperature, therefore, there also has to be a thermodynamic entropy to go with that temperature. And so your T delta S gives you the information and tells you Q, and you end up being able to. And this I liked and was excited about it, because I had always thought that general relativity was not a fundamental theory, that gravity is not a fundamental force. It's an equation of state for space-time, and that's fine. Now, I had a problem before with black holes, but the students loved it so much I used to teach them about it. Now I think black holes are just the way you have a boundary on space-time. So the phenomenon is very simple. If you're near a black hole, you see Hawking temperature coming out. That is just proportional to the surface gravity of the black hole. And if you're an accelerating observer, that guy's supposed to be the solar observer. You also see temperature. And what does this mean? Well, we always saw an equivalence between acceleration and gravity on a microscopic scale, but it also means that space-time itself has structure. Right? You can't have a thermal bath or a thermal effect if you don't have something to excite. Now, they may be virtual photons, or it may be that there are space-time atoms, and that's one of the big arguments is these days. If you do that and work backwards from the Bekenstein-Hawking entropy and temperatures, you can then derive the Newtonian equations, or you can derive the general relativity equations. And so there is something. How does general relativity know about thermodynamics, or how does thermodynamics know about general relativity? Well, there's something that's very deeply linked between the two. Okay, so about that time, I was visiting the IPMU, and I was worrying about the horizon of the universe, and Damien Houston was a postdoc who was visiting. Now, we have one of our colleagues, probably knows him because he's in Arizona, and we're doing that. And Paul Frampton joined us at tea time and inserted himself on the paper. But here's a little cutout of the paper. Say, what's the entropy of the Hubble horizon? Well, you can plug it in, just put the numbers in. It's the maximum entropy. It's 2 times 10 to the 122 K. Right? That's pretty much entropy, but that 10 to the 122 didn't strike me quite yet, but it struck me a little later. And so you can look at the universe and say, okay, what about early times during inflation? Well, that dominated the entropy of the universe. And then the radiation, for some reason, doing it. I'm not sure this is right. I have to go back and recalculate. This is 15 years ago, so and then the cosmic event horizon, it starts dominating, and it gets up to where it's now 110 to the 122, and it's slowly rising after that. And during this time period, we've started to have stellar black holes, and then eventually supermassive black holes. But they're, 10, 12 orders of magnitude at least lower than that in terms of the total entropy of the universe. So in terms of what's going on, that's the dominant thing. But it's interesting that supermassive black holes are coming up that way. So if you say, all right, what if I just increase the radius of the universe a little bit by its expansion? How much does entropy increase? You can just do the derivatives. It's just the delta R over the Hubble horizon. And you can figure out what the force is, and when you plug all the numbers in, it comes out to C to the 4th over G. That's awful simple. You thought it would be more complicated. It would have, but it has just simple fundamental constants. And then you could say, all right, well, what's the pressure? Equation motion, P equals W over. Well, it's 2/3 of the critical density. So then I was excited and all about it. That's when I wrote this paper, and I said, well, this explains the dark energy, right? We'll publish it. We had trouble. It took a year to get it published. And I thought nobody got excited about it, so because there are a lot of other stuff going on. And there's another separate problem, which I'll point out too in the next. Right? So at the same time that we was doing that, Eric Verlinde was proposing a conceptual body of making gravity arrive at entropic force. And this is much harder because he just wanted to put in arbitrary screens and have the information about what's inside projected on the screen, and then you could see it create a force of gravity. It's harder to make a conserved system where you don't have a lot of extra constraints, whereas the thing about the real horizons that I was pointing to, they always have the maximal entropy, and you always have a well-defined kind of system. But one of the things that I point out is that if you really look at what the action should be, there's a term for the volume, which is what most people derive general relativity from, plus a term from the boundary, which is the curvature of the boundaries of space. And it turns out, when you look at those, you can either one of them gives you the same, in most cases, either one of them gives you the same answer. Right? The boundary is telling you the same information that the bulk is. However, there are a few cases where the boundary does give you a different answer because you're forcing the space-time to be a little bit distorted. I found that all interesting, but I didn't figure out how to solve it, and I didn't figure out how to make Verlinde's thing ever work. Okay, but there are people who've continued on, and I just point this out. This holographic entanglement produces space-time. So not only gravitation emergent, but space-time is emergent. And there's a lot of evidence to see that. because one of the things that you see when you do quantum entanglement is that things that are highly entangled are apparently close together in space, and things that are poorly entangled are far away in space. And if you break some of the entanglement, you can actually break some of the connections in space. So there's some reason to think that you might actually not only create and have gravity emerge from stuff, but you can also create space and time. So this is much harder, but it is not outside of reason. But again, there's a lot of speculation and a lot of stuff isn't quite right about it. I wanted to get the quantum computing, then I'll pull the pieces back together, I hope. During the same time frame, not quite the same time frame, a little later, quantum computing made a big leap forward when people thought about how to make error correction. The biggest problem in quantum computing is you make a quantum computer, how do you make sure that errors don't populate in? Because there's a bad environment. They're cryogenically cooled and there's a warm thermal background and you have to make sure it doesn't leak in. And so in 1995, Peter Shor introduced the first quantum error correcting method. And this is unfortunately a little expensive, right, in terms of what you're doing. That is, if you take a quantum computer, which is made up of a bunch of qubits, and you take some of the qubits together as a group and quantum entangle them, then you can connect them to another system and you can sense whether they're staying in a good pattern or not, but without disrupting them too much. So that's the tricky thing. How many guys do you have to put together, right? If you're going to make 1,000 qubit computer, but you got to put them together in groups of 500, it's only a 2 logical qubit computer, right? And so you need to figure out how carefully you can build your computer so to know how many guys you have to entangle in order to make potential error correction. And so there's been a lot of work going on this in recent years, and it's an example of what's going on. So all of these things are physical qubits in a quantum computer. So you made a big array, and you take a bunch of them, outlined in blue, and you group them together, and you have them in zeros and ones, or whatever entangled group you want to have them in. And one of them has a phase flip error, and one of them has a bit flip error. Can you fix this? And the answer is you have to look at your associated entangled group and see does it look disturbed or not, and you can do that. I have, if people want to ask questions, I have an example of how sometimes this works and sometimes it doesn't. You're taking the fact that you can't go in there and arbitrarily reproduce it, but you can probe a little bit. That same question is, can Eve eavesdrop on Alice and Bob's conversation by not perfectly eavesdropping on it, but partially eavesdropping on it? So sometimes you can do this and sometimes you can't. So you have to see your operating system, how good it is and how stable it is. Now the universe solves this problem. The universe doesn't make bit mistakes, right? We think charge is conserved, we think baryon numbers, we think a bunch of things are conserved, right? And so we have this situation, and the original thing when I showed you the picture, the surface of the black hole was divided up into little sort of squarish regions, and there was a bit, and the bit was, every 3/4 of 10 to the minus 65 square centimeters. Really, it's a nice small computer, right? But in reality, here's one that's tiled with little triangles, right? It's 4 of the triangles stuck together in some coherent way. But in fact, it's probably much more complicated than that. It's probably entangled. We believe that all the information that's on the surface of the black hole is all quantum entangled in some complicated way. And how might that be? Well, one of the ways that's very good is to have never repeating patterns of tiles. Okay, and so Roger Penrose invented this, surprisingly. He invented the diamond patterns. This is one example of diamond patterns. There are many examples of diamond patterns. And there's some old Moorish and other tiling patterns you can see where people actually use diamond tiles. And if you can make non-repeating patterns in your two-dimensional space, at least over London, then you have a way of really making different entangled patterns that can check the bits more carefully. So this is a different set of things going on like that. And so I'm going to skip over this because this is talking about how a conformal translation, it's just a translation of time, how the conformal translation can make 2 dimensions look like 3, right? And we're going to do that by using the fact that the same patterns on different scales will behave like there are different distances from each other. They'll interact the same way with each other, but they won't. They'll look further away and further. And you can think about a spherical system and tile it different ways. You can do different kind of stuff. And on the outside, you got these patterns. On the inside, you think you have galaxies. It's not a whatever. So I'm finally to the end here. An ideal quantum computer will have the properties that the universe has. Right? The universe is very careful. You can't hide the data, information. The problem with the quantum computing is sometimes the information could go out into the thermal environment around you because you've built an isolated system, and you do that. But you would like to have these either non-repeating tiling or complicated kind of things in order to make these kind of things operate. You want to have the same kind of patterns that the universe has on its boundaries, on what you think of as a boundary, the 2 dimensions on the 3. You want to have those same kind of patterns. And the universe has already all the properties that you want for a quantum computer. In fact, it's clear the universe is behaving very much like an ideal quantum computer. It's just, all its properties are doing the right things. So that's where I'm going to stop, because I already ran over a couple of minutes. Thank you.